Welcome to The Explainer. Today we're going to break down something pretty amazing, how a humanoid robot can pull off walking and using its hands at the very same time, all without face planting. Let's get into the elegant solution that makes this whole complex dance possible.
All right, so let's get right into it. For you and me, walking and grabbing something is, well, it's nothing, right? We do it without even a single thought. But for a bipedal robot, this is a huge, huge challenge. It's a classic case of trying to manage two goals that are fundamentally fighting with each other.
You see, it's like this constant internal battle. On one side, you have the absolute top priority, the must-do, which is don't fall over, non-negotiable. But on the other side, you've got the mission, the wants-to-do, like reaching out to grab a box. And believe me, these two objectives are always at war for control of the robot's body.
And that right there, that's the absolute core of what we call whole body control. How in the world do you resolve this never-ending conflict between just staying upright and actually getting the job done? It's a real juggling act.
Exactly. You can't just tell the robot, hey, go grab that box. If its arm shoots out too far or too fast, its center of mass is going to drift right outside its feet, and, well, you know what happens next. Timber. So it needs a way smarter method for making decisions. So, instead of trying to kind of duct tape a walking controller and a grabbing controller together and hoping for the best, the modern, elegant solution is to use one single unified system, a master controller that thinks about every goal and every physical limit all at once.
And this is where some really cool math comes into play, a powerful technique called quadratic programming, or QP for short. Now, don't let the name scare you. The easiest way to think about it is as a master negotiator for the robot's body. It listens to all the competing demands, stay balanced, move your feet, reach with your hand, and finds the one perfect compromise that gets the job done without, breaking the laws of physics.
Okay, but here's the part that'll really blow your mind, the speed. This whole negotiation process, this entire loop, from deciding the goal to actually commanding the motors, it repeats 500 times every second. That's 500 hertz. The robot is constantly reevaluating and reoptimizing its every single move in real time.
Right. So, if you're making 500 complex decisions a second, you better have some clear rules, right? You have to know what matters most. And that's exactly how our master negotiator, the QP solver, works. It uses a super strict hierarchy of priorities.
And this right here, this is the prime directive, the one rule to rule them all. Balance is never sacrificed for manipulation. It's like the first law of robotics, burned right into the controller's DNA.
And this just shows you how serious that rule is. We're not talking about a gentle suggestion here. Look at the numbers. The balance task gets a priority weight of 1,000. The hand manipulation task, just 10. So balance isn't just a little more important. The math is literally screaming that it's 100 times more important. It makes it crystal clear, a stable robot that fails the mission is infinitely better than a toppled robot that tried too hard.
So here's the whole stack, the whole pyramid. At the very top, with that massive weight, critical priority, don't fall. That gets first dibs on everything the robot does. Then, with whatever freedom of movement is left over, it worries about placing its feet correctly. And only after that's taken care of does it even think about moving its hand. That last one, posture, that's just a nice to have if there's literally nothing else to do.
So you've got the theory, the math, the priorities, but how do you actually build this thing? Well, you don't just flip a switch and have it work. You have to build up the skills carefully, phase by phase.
And the development was done in these really smart, deliberate steps. It's kind of like learning to be a human, right? First, you just master standing still, get that balanced down. Then in phase 2, you introduce the QP solver to try reaching while standing. Once that's solid, you bring in the walking controller from previous work. And only at the very end in phase 4 do you plug it all together for the grand finale.
And this is what it all leads to, the capstone pipeline. You can think of it like the robot's mission script, and the high-level state machine is the director of the whole show. It calls out every shot. Okay, walk to the table. Now, stop and get stable. Now, reach. Every single step is its own carefully choreographed scene in the performance.
And check this out, because this is one of those little details that just shows how incredibly sophisticated this is. The instant the robot's gripper closes on that half-kilo object, the controller doesn't just feel an extra weight. No. It instantly updates its own internal body model. It says, okay, I'm heavier now, and my combined center of mass has shifted, and it recalculates its balance target on the fly to stay perfectly stable. It's not just reacting, it's being proactive. Okay, so Why? Why go through all this trouble, all this complex math, this careful phased development? What's the big payoff? Well, it's all about building a solid foundation, a bedrock for everything that comes next.
And you can see right here, this work is a true culmination. It's like the greatest hits album of all the previous research. It's pulling in core concepts from dynamics, from grasping, from state-machine coordination, and from bipedal walking. And it masterfully integrates all these separate parts into one unified, highly capable controller. It's the whole shebang.
And here's the crucial takeaway. This whole thing isn't just to make a cool demo video. The whole point is that this controller acts as an expert demonstrator. It is the robot equivalent of a flawless Olympic performance. It's the gold standard, the textbook execution of how this task should be done perfectly according to the laws of physics.
And that all leads to this final, absolutely fascinating question. You now have a robot that has truly mastered the physics of its own body. It's a perfect athlete. So, what happens when you use that perfect athlete to teach an AI? This expert controller becomes the teacher. It provides the perfect demonstrations for the next step, which is training an AI to do all this same complex stuff, but just from watching and listening to commands. This physics-based controller, it's the key to unlocking the next generation of truly intelligent robots.